try another one. All right, so we're on 3A.1. This is going to be a three-part notes, and we are talking about exponential with natural base. What natural base is, it just means that your base is an E. And what is E? E is just a number, okay? And you guys remember pi, right? And pi is just a number, correct? Even though you're like, oh, no, there's a pi. No, pi is just a number. So let's talk about how they came about with E. So with E, someone was like, okay, let's test patterns and see what happens. This is not in your notes. It's just um, and math is all about patterns. So if some really bored person sat and was like, okay, I notice when I plug 1 over n, I get this. I notice when I take that and add 1, I get this. I wonder what happens when I put it to the nth power. Well, let's see. And then you start to notice that it starts to become the same number, and the number just keeps building on and building on and building on. And then that's, my friend, where E comes into play. So if you are on the calculator and you see a button that says E, it's going to usually be with natural log. And that's because it's the natural base. All right. So as you can see, when you put it in the calculator, this is what you're going to get for the value. All right. E is just a number. Capiche? All right. So therefore, when we talk about it as a base, an exponential base, we're going to treat it as if it was a 2, a 3, a 4, or a 5. You're still going to follow the same rule, which is plugging into the power. So plugging in the power and then analyzing. So it would be e to the negative 2, e to the negative 1, e to the 0. And the 0 rule is anything to the 0 power is 1. E to the 1, e to the 2. And just like any other time, you have an input and an output, an input and an output, an input and an output, which leads to a graph, right? An input and output, when I plot it, that's my X and my Y of my graph. And this is what you end up with is your exponential with base E, natural base E. Okay. So let's talk about attributes of all exponential functions. So not just E, but all exponential functions. All exponential functions have the same general parent functions have the same general rules, meaning that attributes, not rules, attributes, that if I have a exponential function and your base is greater than 1, that is going to be a growth. And it's going to be an exponential growth because your base is greater than 1. What that means is that when I look at the graph from left to right, it's going to be increasing. Make sense? Remember that? Bring it some else. Okay. The values here just all depend on whatever your A is. So whatever A is, these points are going to change, but the shape and what it looks like is going to stay the same. Okay. You're going to have your asymptote. You're going to have your y-intercept at 0, 1. And that's going to be the same for all parent functions with whatever base it may be. All right. So when we talked about the domain, this function goes forever to the left and forever to the right. So your domain is negative infinity to positive infinity because it's all real numbers. Your range, the interval for your range, it has a boundary line. It has a low point, but it goes forever. So my low point that I can't cross is 0, and I go forever to infinity. So my interval is going to be from 0 to infinity. And with 0, it's parentheses, not bracket, because it's an asymptote. It can't be included. Remember, if you can't see or you're in a position that's uncomfortable to see from, you can always open your canvas to look at the Zoom link. All right. Our x-intercept doesn't exist because we can't touch the x-axis, and our y-intercept, as we said, is at 0, 1. We have our horizontal asymptote. Our horizontal asymptote happens, and it comes into play as our x's go towards negative infinity.
Means we're writing the black parts.
Uh-huh. Do you see like the difference? Be like tiny blanks. No, like a box.
Oh.
Okay. And then, like we said before, the graph is increasing. Does anyone remember what it means to be a one-to-one function? What makes a function one-to-one? No takers? Okay. A one-to-one function means that there are not only no repeating x's, but no y values repeat. Okay. In general, most people want to be in a one-to-one relationship, right? I'm not dating anyone else. You're not dating anyone else. We're only dating each other. Okay. That's what a one-to-one function is for every X, there's only one Y, and for every Y, there's only one X. So when you look here visually, that means not only does it pass the horizontal line test, it also passes, I'm sorry, the vertical line test, it also passes the horizontal line test. When I go horizontally across, I'm only hitting 1 point at a time because none of my Y values are repeating and none of my X values are repeating. So it's a one-to-one function. All right. It's going to be smooth and continuous. Continuous just means that I can trace it without lifting a finger. All right. Do you think much is going to change if it's less than one? What's going to change? There's only one thing that changes. It's going to be is going down. It's going to be decreasing because this is a when your A value is between 0 and 1, that means you have a decay. So when you read from left to right, like we read graphs and books, it's going to be declining. It's going to be decreasing. Everything else is going to be the same, except that little attribute is what changes. So my domain is still negative infinity. My range is still 0 to infinity. My x-intercept is still none because of the asymptote. My y-intercept is still at 1. My horizontal asymptote is going to change because my horizontal asymptote comes into play now instead of heading towards negative infinity when I head towards positive infinity because that's where the decrease is heading to. And our graph is now decreasing. So when you are comparing the difference, it's your horizontal asymptote still exists, but where it's heading and that it's increasing. And then your horizontal asymptote is heading towards positive infinity and it's decreasing. Everything else is the same. All right. This last little tidbit ended up on the wrong page, but we're just gonna go ahead and go through it because it's on the wrong part of the notes, but it's all right. Here we go. So at the bottom is like a random little fact. If the bases are the same and you're trying to solve, all you're gonna do is solve, all you're gonna focus on are the powers. So if the bases are the same and you're trying to solve, all you're doing is focusing on the powers. So an example would be if I have b to the x and b to the x equals b to the 2. Therefore, the bases are the same. So my solution is simply x equals 2. Does that make sense? So if the bases are the same, when you're solving, you don't have to worry about anything else except taking your exponents and setting them equal to each other. And 9 times out of 10, that takes it and turns it into an algebra 1 problem. So we'll take it from being a algebra 2 or higher problem and turn it into a basic algebra 1 problem. Like all you're saying is, how can I make these two look the same? Okay. All right. Transformations. So in your review last class when you were going through, a big thing was you reviewing the transformation rules. And that's because transformation rules do not go away. They are utilized the entire year in Algebra 2, okay? Because we use them with every function. So this one, we're going to look at the transformation rule specifically as an exponential transformation. And we're going to look at it as an exponential transformation where the base equals E. So we're going to have our base equal to E. So what this will look like is y equals a times e to the x minus c plus d. Okay. And as we hopefully reviewed last class, is that every transformation variable plays a role, correct? Your a, your b, your c, and your d is telling you this function to do something, correct? Yes. All right. So, starting here on our D, your D is your vertical translation, right? I'm gonna put a V for vertical because it's telling your graph whether it's gonna go up or down. If you are adding D, it's going up. If you are subtracting D, it is going down. Okay. D is also your horizontal asymptote. So for when this problem happens, your D is your horizontal asymptote. If there is not a D, then your horizontal asymptote is still at 0. Does that make sense? Okay. Now let's talk about C. C is your horizontal movement. So I'm going to put an H for horizontal. Your C is telling you whether you're going left or right. What we need to remember about C is that C is a liar. Okay. We see minus and we assume that we're going to the left. But actually, when you see a minus, that means you're going to the right because if C is positive. When you see a positive, a plus, that means you're going to the left because it was a negative, and a negative times a negative makes a positive. Did these rules really change from a function to a function? Mm-mm. All right, now we're going to talk about our A. So your A, the guy out front, the factor, your coefficient, your stretch and compression together, those are called your dilations. So those are your two types of dilations. You can have a stretch dilation or you have a compressed dilation. Okay. All right. So absolute value of A, meaning ignoring if it's negative. If the absolute value of your A is greater than 1, then you have a vertical stretch. Okay. That means that all of your Y values, you would take your A and multiply all of your Y values by A. And they're going to increase because they're going to stretch. If your absolute value of your A is between 0 and 1, that is a vertical compression. They're going to shrink. So again, you're taking your A and multiplying all of your Y's, but this time they're going to do what? They're going to decrease. They're going to get smaller. Pretend that that says decrease. Okay. When you look at your A as a whole number, as a whole integer, I'm sorry, is where it's used. If it is less than 0, meaning that it is negative, that is when it's going to reflect. And being negative means that you're taking your Y values and you're multiplying all your Y values by -1. So that meant if my Y is negative, a negative times a negative makes a positive. If it's already positive, then it's going to become a negative. I've seen kids like do a reflection and they'll leave Y values alone that are already negative. I'm like, why did you do that? Like, well, it was already negative. Yeah, but you're multiplying it by -1, which meant that if I'm already negative, I'm going to become a positive. Okay. All right. Questions about the transformation rules for exponential model? No? All right. So let's talk about and apply them. So if I asked you to describe what's happening here to the graph of f of x equals -e to the x minus 3, and then determine the domain, the range, and the horizontal asymptote here, could you tell me? Only you can answer that, and I can't answer it for you. What variables are given to me? What transformation variables are given to me? F of x is the function, so that's not it. What's different? What has been added on to the e to the x? Huh? I have a negative. These are my changes. I have a negative in front and this -3. Those are my changes. Those are my transformation. Okay. From those transformations and me looking at my chart, I'm like, okay, well, if I have the A and I have the C, I'm going to follow what rules it says. Does that make sense? So I have my A and I have my C. So I know that A equals -1, and I know that C equals +3 because X's are what? Liars. And even though it looks like it's a negative, it's actually a positive. Okay. What is that -1 telling me? It's going to reflect. So it's a reflection over the x-axis. And that 3 is telling me what? Which way? To the right. It is 3 units to the right. Do you see how we dissected it? Yay, nay. Okay. That's all you're doing is asking yourself, how did it change? Okay. So the next part is to graph it, right? So here is the paired function. So this is your original e to the x. So you're doing these transformations to that original function. All right. So here's my original. To my original, I know that I have to reflect over the x-axis, which means that all of my y values have to be multiplied by a what? What do we say if we want to reflect? We have to multiply y's by what? A -1. So all of my y values have to be multiplied by -1. So you're going to be multiplied by -1. 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 On yours, you just have the blank graph so you can do it all at once. All right. The C is my horizontal, which means that it's affecting my X, right? So to all of my X values, if I need to move them to the right 3 units, what am I going to do to them? I need to move something to the right 3 units. What mathematically am I doing? I'm adding 3. That's it. I don't know what y'all were thinking or if it was just squirrels running through your brains at that moment. But you're just adding 3. If I need to go 3 units to the right, I'm on a number line. So I'm going to add 3 to each one of these. So to each X value, I am adding 3 units. Those new points are going to be what I'm graphing. Does that make sense? Okay. Your parent function isn't going to change. Your e to the x just means I have no transformations. So if I'm adding to each one of these, my new locations, so currently I'm at -2. -2 plus 3 is going to put me where? At where? -2 plus 3 is going to put me at +1, right? You owe me $2, you have $3, you're left with $1, right? Okay, my y was positive. Now it's going to be negative. -1 plus 3 puts me at 2. My y was positive. It is now negative. 0 is going to still, 0 plus 3 is going to put me at 3. My 1 was positive. It's now negative. 1 plus 3 puts me at 4. This was positive. It is now negative. And then 2 plus 3 is 5. This is positive. It is now negative. Do you see now how I have the points to do my graph? Okay, so then I would do my graph. And once I do my graph, then I have all my attributes in. What I did need to note is that because there's nothing being added on, your D is still at 0, which means that your horizontal asymptote is also still at 0, right? Because it didn't move. Okay, so when I'm done graphing, what should that look like? Because I would like to believe that at this point we all can graph and plot points. No? Yes, maybe so. So here, and then once I've done everything, my graph is now due, and it's going to be reflected down. For me, it helps to make the table first and then plot my points when I'm doing a transformation. Some people can do it as they're doing it, but for me, I like to do the table and then plot the points from the table. Questions about plotting the points or creating the graph? Oh, yeah. No questions, comments, concerns? All right, so let's kind of look at it. So recapping, we had our parent function. We knew this was the parent function because if we were taking away the things that are added, we would have been at y equals e to the x. Next, we noticed that our a value was negative. Because our a value was negative, we had to multiply all of our y's by -1, which caused it to reflect, right? After we did that, we noticed that our x minus 3, we have that 3. X's are liars, so that means that we're moving 3 units to the right. So to all of our x values, we added 3, and then this is why we ended up here. Yes? So that's the summary of what took place. All right. When you're doing transformations, it is helpful to make sure you understand what variables you're given. Are you giving your A, your B, your C, your D? And then to explain to yourself and justify what they are and how it's going to be affected. If you have your notebook from last semester, you're looking at pages 46 and 47 for that all together little cheat sheet and reference sheet. Okay, that concludes part 1.